A block is sitting on an incline that makes a 30-degree angle with the horizontal. The block is just about to slide down the incline. What is the friction coefficient between the block and the incline? So let's start by drawing a diagram for this. So here we have the incline, and this is the angle of the incline. We're going to call that theta. So let's say that this is the block. This little dot here is the block. So let's draw the free body diagram and label all the forces. So pointing perpendicular to the ramp's surface, you have the normal force that's keeping this block from falling through the incline. And pulling it up, you also have the force of static friction, because it is just about to slide down the incline, but something is preventing it from sliding down, which in this case is the force of static friction. Now down you have the force of gravity, or mg. And this can be split into a horizontal component that's it's kind of horizontal. I should say that a component that's actually parallel to the ramp, and a component that is perpendicular to the ramp. So these two will form a right angle. I know this is not the best drawing, but it's a general idea. And then this angle will be theta here. And then here, if that angle is theta, this angle will be mg sine theta. So that force is mg sine theta. This is the force that is parallel to the incline surface. And this force will be mg times the cosine of theta. And this will be the force that is perpendicular to the incline, and the one that is kind of creating the normal force. So now that we have everything, we can write down a few equations. So first, we can say that the force of static friction is equal to the coefficient of static friction times the normal force. But we don't know what the normal force is yet. So we can figure that out by looking at this diagram. So from here, you can see that the normal force minus mg times the cosine of theta, since they're both perpendicular to the inclined surface, is equal to the mass times acceleration of the block. But since the block is just about to slide down, that implies that it is currently stationary. So the acceleration is 0, therefore the whole side is 0. So from that, we see that the normal force is equal to mg cosine theta. And then you can plug that in a moment. So from that, we can say that the static friction force is equal to the coefficient of static friction times mg cosine theta, as that's the normal force. Now we also can write another equation by using the forces that are both parallel to the incline. From this, we can say that the force of static friction minus the component of gravity that is parallel to the incline, or mg sine theta, is again equal to the mass times acceleration, which is 0. There's no acceleration. So the force of static friction is equal to mg sine theta. And then from that, we can substitute this for the force of static friction to get that the coefficient of static friction times mg cosine theta is equal to mg sine theta. It is a bit squished, but that is what we get if we substitute coefficient of static friction times mg cosine theta into the force of static friction. And now all we really need to do is to simply solve for the coefficient of static friction. Both of these cancel each other out, so you end up with saying that the coefficient of static friction is equal to the sine of theta divided by the cosine of theta. And you might remember that that is, hold on, let me erase all of this. Might remember that that is simply equal to the tangent of theta. Okay, so now that we've got that, we can plug everything back in. equal to the tangent tan 30. And this is simply sine 30 over cosine 30. So this sine 30 is 1 over 2, cosine 30 is square root 3 over 2. This simplifies to square root of 3 over 3, which we can approximate it to 0.58. So the coefficient of static friction is about 0.58, and it doesn't have a unit. So this is how you would solve this problem here.